Hi, welcome back to AT Math. Today, 8-1, factors and greatest common factors. Why more intriguing than this optical illusion? Okay. Now, factorizations, what does it mean? It's the different ways you can split up a number into factors. Simply put, if I take 12, well, what times what makes 12? Well, you have 1 times 12, or 2 times 6, 3 times 4, or even 2 times 2 times 3. All those bits, if you multiplied together, would make 12. So they're all factors of that. Now, a prime factorization is the factorization that breaks the numbers into the smallest pieces. So of these four choices, this is the smallest bit because we can't break 2 and 3 any lower. They're as small as they're going to get. You can't divide them any smaller, unless you want to divide it by 1, and that would be the only way. So this is the smallest it gets, therefore it's the prime factorization. Now let's review a factor tree. Take 16 and take 12. 16 breaks down a couple different ways. You could have 4 and 4, 8 and 2, or whatever method you prefer. But in the end, you're going to get 2, 2, 2, and 2. A 12 will break down to 4 and 3, or 6 and 2, but in the end result, it'll be a 2, 2, and a 3. You know this, by the way, because if you multiply all these guys up, you'll get 16. If you multiply all these guys up, you'll get a 12. Notice how in each case we simply divide down to the smallest numbers. Well, okay, that's no major strain here. Well, besides a factor tree, we also have a ladder diagram, also very popular with Algebra 2, so I want to show you this now. As the factor tree goes ahead and splits 16 into smaller bits, the ladder tree does the same, but you get to pull out prime factors like 2 and so on. Notice how with the 16 I pull a 2 out and I get 8. Pull a 2 out and get 4, pull a 2 out and get 2, pull a 2 out and get 1. And so I have 4 2's this way or 4 2's that way. Either way, it's 2 to the 4th power. The results are the same. Now you try. Make me a factor tree and a ladder diagram of the following. Go ahead. Let's see how you did. Well, in my case, for the factor tree, what I would do is I would go ahead and say, well, 120 I could say is a 12 and a 10. Because I could say, okay, that's 12 times 10. And from there, I'd say 12 makes, well, a 3 and a 4. And 10 we'll say makes 2 and a 5. 2 and 5, by the way, are prime numbers, therefore the train stops there. 3 is a prime number. 4 breaks down to a 2 and a 2. Notice here how we have 3 2's, so 2 to the 3rd power, 1 3, and 1 5. And if you took 2 times 2 times 2, which would make 8, times 5, which is 40, times 3, which makes 120, we know we're in good shape. The other way, you take 120, I can pull out a 2 and get 60, pull out a 2 and get 30, pull out a 2 and get 15, pull out a 3 and get a 5, and pull out a 5 and get a 1. Both are just as valid. This shows 3 2's, a 3 and a 5. This shows 3 2's, a 3 and a 5. So either way is good. Now we want to find the greatest common factor of two numbers. So let's say 16 and 42. 16 breaks down to a 4 and 4, which breaks down to a 2, 2, 2, and 2. 42 breaks down to a 6 and 7, which breaks down to a 2 and a 3. Now if you notice, I have 4 2's here. I have 1, 2, a 3, and a 7 over here. To find greatest common factor, you match up the numbers that are in both groups. In other words, what's the same? Well, the only thing that's the same between these two is a 2. So the greatest common factor is a 2. What does this mean, by the way? This means that I could divide 16 and 42 by a 2, and that would be it. Because look what I have here, the same thing. I'm going to divide both by a 2. 16 over 42 becomes 8 over 21, and we're done with that. We cannot break it down any further because there's no factors that are shared between 8 and 21. You go ahead and try. Find the greatest common factor. Go ahead. Let's see what you did. 18 and 24. 18 breaks down to a 3 and 6. 6 breaks down to a 2 and a 3. 24 breaks down to a 4 and 6, and 4 breaks down to 2 2s, and 6 breaks down to a 2 and 3. Long story short, the 18 has a 2, 3, and 3, and the 24 has a 2, 2, 2, and a 3. So what's the same for each one? Both seem to share a 2 and a 3. Therefore, 2 times 3 is 6, so the greatest common factor between these two is 6. It's true, by the way, because if I divide both by 6, notice how I get 3 over 4. And that's as small as it can go. One more real quick. 18 and 54, go ahead. Did you get this? 18 breaks down to 2, 3, and 3. 54 breaks down to a 2, 3, 3, and a 3. Both share 1, 2, and 2 3s. So 2 times 3 times 3 is 18. Now you might say, wait a minute, this whole number is 18. Well, that's true. But you can take 18 divided by 18. Therefore, the greatest common factor is 18. If you had 18 over 54, it would become 1 over 3. Quick break.
Peel my paint off or something. Oh my gosh!
Yeah!
And back. Now you already knew all that, but now here's the Algebra 1 part. Take 3x cubed and 6x squared. We're going to break it down the same way, but this time 3x cubed, put 3 over here, x cubed over here, and they break down to 3 single x's. 6x squared, well, 6 breaks down to a 2 and 3. X squared splits into 2 x's. Therefore, what's the same? Well, looks like there's a 3 in both of these guys, and there's at least 2 x's in both these guys, so it would be 3x squared is the greatest common factor, meaning if I were to divide both of these guys up, I'd find a 3x squared. I could divide by a 3x squared, excuse me. You try, find the greatest common factor. Go ahead. Did you get this? Because I could, when you broke it down, did you able to divide both by 3 and pull at least 2 y's out? Hope you did. Another quick break. And back. Garrison is creating a web page that offers electronic greeting cards. He has 24 special occasion designs and 42 birthday designs. The cards will be displayed in the same number of designs in each row. Special occasion and birthday designs will not appear in the same row. How many rows will there be if Garrison puts the greatest number possible of designs in each row? Let's first understand what they're asking, because year in and year out, people have questions with this. And by the way, you can follow along on page 526, example 4, which would be, let's see here, right here. So if you want to follow along, you can. Now, what I would suggest is this. Garrison needs to have each row be equal width, though it does not matter how many rows there are. For instance, if I have so many rows, I'll say there's 42 birthday designs on these rows. And then these rows below will have 24 special occasion designs. What I don't know is how many to put across in each row. Well, how many row? What we do is find the greatest common factor. So take 24 and 42. Let's break it down. 24 gets to be a 2, 2, 2, and a 3. 42 is a 7, 3, and a 2. It looks like there's both a 2 and a 3. Therefore, 2 times 3 is 6. But be careful. 6 is not the answer. What 6 is how many I can put across on each row. Each row can have 6 across. If I want to be able to have them go all the way across without having an overlap or one extra, I want to have 6, 6, 6, 6, 6, 6 all the way down. The only question is how many rows will I now need? And that's what I need to know. As I said, it's not 6, but how many I put in each row. So I can put 6 in here. And since I have 42 birthday designs, I'm going to have 7 rows of 6 to make 42. And with 6 across, I can have 4 rows of 6 to make 24. The actual answer is 7 rows and 4 more rows, which make 11 rows. And that's the answer. And we are done. Thanks again for watching. Hope this helps. We'll talk to you tomorrow. Bye.